Okay, for this problem, you want to realize that it's an impulse problem because there are impulsive forces when these two balls collide. And so you approach it in kind of the standard way. In this particular case, because it's moving in two dimensions, it's important to identify the two important directions. The first one is the direction of if you connect the at the point of impact, if you connect up the centers of curvature, that defines the normal direction. So I'll label this as the normal. And then perpendicular to that is the plane direction, or whatever you want to call it. So this is in the plane of the impact. So those are your two directions. As usual, what you want to do is choose a system that has the zero impulsive forces on it. So I'm going to choose bodies A and B, and I'm going to apply the momentum equation. So I have impulse for the two of them together. The impulse is equal to 0 because the impact force is inside the two systems. All right, and so this is according to Newton, the impulse is equal to the change in momentum. So I'm going to apply the change in momentum along the normal direction. So at the end, the velocity of B, they say, is along this line, which is 30 degrees counterclockwise from the vertical. So B is going to move along that guy. This is 30 degrees, and the B has got some speed. We'll call it VB right there. So the VB is pointing in that direction. And so after the collision, the momentum is the mass of B, which they're both 0.5 kilograms. 0.5 times the velocity of B in the normal direction. So in this case, it's going to be a minus VB times the sine of 30 degrees, and that's the component of momentum or velocity in the normal direction after the collision. After the collision, A, I don't know what it's doing, but I'll say that in the normal direction, I'll say I think he bounces back to the right, so that would be a positive 0.5 times the velocity of A in the x direction, and we'll say final right there. Maybe I should put an F on this VB to say that's final. That's the velocity of this guy after the collision. All right. So and I don't know which way VA is going at the end. I'm just going to solve for it, and if I get a positive, that means I'm correct. It's going to the right. Negative, I'm wrong. But anyway, okay, and then I subtract off the initial momentum. So this is the final momentum. I'll put parentheses around there. There's the final momentum minus the initial momentum. The initial momentum is mass of B times the initial horizontal velocity of B, which is going to be 3/5 times 4. And it's in the positive x direction. And for the momentum of A, I have mass and his initial velocity, which is a negative. That's why I put a negative here in front, -6. So that's the final minus initial momentum. If you look at the unknowns, I don't know this number, and I don't know this number. So I have two unknowns and only one equation, so I have to write another equation. Now, the next equation is the coefficient of restitution equation. Let me take a moment of break here. Okay, so to apply the coefficient of restitution equation, The coefficient restitution equation looks like this. So it's the coefficient equals, and this will be it's the final velocities divided by the initial velocities, and it's in the normal direction only. Don't ever apply this in the plane direction. So it goes, and it's one minus the other. It doesn't matter which one you start with. So what I'm going to do is say, all right, I want the I'm going to take B, let me just write it out. Velocity of B in the normal direction, which is the x direction, after the collision, minus the velocity of A in the x direction, which is normal direction, after the collision, divided by, and now I do the initials, and reverse the A's and B's. So if you started with B before, then start with A. So this would be velocity of A in the x direction initially, minus the velocity of B in the x direction initially. Okay, or I think your textbook uses a negative in front, but it's essentially the same equation. However you can remember it or put it in your notes or whatever. So I'm going to plug into this. So the coefficient restitution equals velocity of B in the x direction afterwards. Well, that's going to be V B F times the sine of 30 minus VA after the collision. I think it bounces back to the right. So it would be VA X F divided by, now I do the initials. So the velocity of AX initially is a -6 minus velocity of B in the x initially is equal to 3/5 times 4. Okay, so now I've got the VBF has been counted, the VAXF has been counted. The only other thing that's unknown is the coefficient. So that's 3 unknowns and 2 equations. Have to keep going. In this particular case, because of the 2 dimensions, what you can do is try to apply impulse in the y direction. An easy way to do that is by separating the balls off. So let me show you a free body diagram of that. So if you draw body B, and while it's in contact, in only body B, you have this big, huge, impulsive normal force that's coming from the A's hitting it. But it's only in the x direction. So if you look at impulse in the y direction, there's no impulse. So the impulse is equal to 0 in that direction. Well, if there's no impulse in the y direction on body B, you can apply impulse and momentum. So what you can do is you can say the impulse for body B, 0, is equal to final momentum in the y direction minus initial momentum in the y direction. So we'll say final momentum in the y direction, mass, and we're only looking at B now. The mass of B times the final velocity of B, that'd be VB final times the cosine of 30 degrees. That's the final momentum. The initial momentum in the y direction is 0.5 times the y velocity, that'd be 4/5 times 4. So that's a third equation you can then use for the other. Just for kicks, you can do A as well. I mean, we have enough equations now, but if you apply A, here's the free body diagram of A. It has this big, massive impulsive force only in the x direction because it's a normal force. And so that means that there's no impulse in the vertical. So you can write an equation for that and say 0 impulse in the vertical equals change in momentum of A in the vertical. So that at the end, we'll say, okay, the velocity of A, okay, momentum, mass, 0.5, the velocity of A, final in the y direction, that's the final momentum in the y, minus the initial momentum in the y, it has none. And so what this equation tells me is that the velocity of A final in the y direction is equal to 0. Now, if you're a pool player, you'll realize that that's not true. When you do a glancing blow on these pool balls, there will be a vertical. The reason for that is that in pool billiards, there's friction between the balls. But in this particular case, if there really is no friction, then there's nothing that will cause body A to begin to move in the vertical. So it's a little mind-boggling, perhaps, but it's a artifact of the fact that you're assuming no friction between the contacts. So anyway, if you try to summarize it, let me summarize this. There's 3 equations. The equations are, let's see, right here, this is 1. The second equation is right here. And the third equation is right here. And I have 3 unknowns, so I can solve it. What I'll do is I'll pause and bring it up in Mathematica and show you how to solve this thing. Okay, what I've done here is opened up a Mathematica window, and I have, what you haven't seen is that I've typed in this angle A&G to be 30 degrees just to make the typing easier. Let me enlarge this so it's easier to see. I then, well, that might be a little too big for you, but there we go. This is not too bad. So then I've typed in, without wasting your time, I've typed in the equation. So here's equations are equal to, and the first one is the first equation, which is over here on the, it's this equation. So it's 0 equals 0.5 times, and so I've just typed those in. And then comma, here comes the second equation, which is this one right here. And then the third equation, which is that one right there. And so the first right there, second equation is right here, and then the third one is right there. So what I'm going to do is execute that. So I hold down Shift and hit Enter, and so it tells me what my equations are, and then I simply say solve, and I want to solve the EQ, and the variables are V, B final, VAX final, let's see, and E. Hit enter, and there we go. E is a negative. I'm going to pause this and figure out why that's a negative number. Okay, I have made 2 mistakes. Let's go back over here to this one. If you look in the coefficient of restitution equation right here, in the numerator term, I should be taking the velocities in the normal direction, which is the x direction, after the collision. Well, if you notice, velocity of B after the collision is moving to the left, and so this right here should be a negative number. So I should have a negative right there for the velocity of B final. So that was one mistake that I made. The other mistake is over here in the Mathematica. There was so what I've done is I've changed it. So right here, if you notice, I put the negative in there. The other one was this velocity right here was it's 3/5 times 4. That's the initial velocity of body B. It's 3/5 times 4. What I had originally typed by mistake was 3/4 times 4. So those were the 2 mistakes I had made. I knew I had made a mistake because the coefficient of restitution ended up being negative, and so I knew that was a mistake. So I'll execute this. Those are the correct equations, and then I solve the equations, and so I end up with the right value. If you notice, the velocity of A after the collision is a negative number. The negative tells me that my assumption was incorrect. I assumed that it went to the right. I'm incorrect. It goes to the left. So A kind of follows through, if you want to call it that. So that's the solution to 1588.